We live? Hello, and welcome to yet another online session of Chai and Why. On the first Sunday of the month, we should have been at Prithvi Theatre. Unfortunately, large gatherings are still not allowed, and I figured that Chai and Why actually counts as a large gathering, which in a way is nice to know. So we will be online. And as many of you had asked us, we've had requests to do these simple experiments, which could be done at home with things around. And we've decided this session is going to be on balloons. So I hope you've got, if you're following us and you want to do some of these experiments, have gone and got yourself a few balloons and you know how to blow a balloon. Let me try. Oops, okay. That wasn't the way it was supposed to happen. Let me try again. Okay, a balloon. A little piece of rubber filled with air can be just so much fun. This is something which all kids, we enjoy. We've seen these balloons, but balloons have been around, and balloons have had many uses all through history. And if you followed our Facebook or Twitter, my little blurb, I had written that balloons were used for aviation. You know, remember hot air balloons? Balloons are used for advertising, and balloons were used for angioplasty. And then that was just the A's. But you know, balloons are used for, let's see, B for maybe birthdays. C for, do we have something with a C? Yeah, maybe catheters. Catheters, of course. Balloons are used for communications. Google wants to connect these Project Loon with balloons. With D, you can have decoration or displays. In the Commonwealth Games, you had this huge balloon on which they were projecting things. It's called an aerostat. And all that, and it's used for pretty much, you find balloons in so many places. Your football bladder or a car tire is effectively a air packed into a balloon-like thing. And most importantly, we use a lot of balloons for high altitude experiments, and we will get to that eventually. But forget those big balloons for high altitude experiments. What we are going to look at are experiments with these very simple balloons. So the first thing is, how do you blow your balloon? Typically with your breath. It's always hard to get it started. Once you get it started, it's usually a little easier. But maybe it is difficult to blow a balloon with your breath. So maybe we should make a little pump. So in case you have difficulties with blowing a balloon with your lung power, you can get yourself a pump. This could be a little pitchkari-like thing. It could be a cycle pump, but it's very easy to make pumps. And by the way, I should acknowledge that many of the experiments we'll show you today are all, there are brilliant videos available on the net by Arvind Gupta. Arvind Gupta ji has done so many wonderful experiments and toys with balloons. We will be probably able to do a very small fraction of them. So if you just go to arvindguptatoys.com or Google Arvind Gupta and balloons, you'll get a whole list of things that you could do. But first, let's see if we can make a little pump. Okay. So, and you can make a little pump with nothing more than a empty bottle. Okay. And let's see, where is Suren uncle hiding? We need Suren uncle. You're here. Okay, we need to make a bottle. We need to make a pump with a bottle. So let's just show you very quickly how you can make a pump with a bottle in case you need to do that. So are you going to do the cutting over here? Then I will cut it there. So let me, as you know, we have this one webcam that we use to do this. So I'm going to try and see what, okay. So what he's going to do is he's going to make 2 holes at the side of the bottle. So just with a scissor, 2 holes at the side of the bottle. Okay, that's 1.
And make them square.
And cut them out, cut a little, squarish or whatever you can cut. It doesn't have to be perfectly square. So we just cut two. That's one, and
is the small cut piece.
There's a cut piece. So there's the little cut piece that we brought out of it. So there are two little cuts at the sides of a half a liter plastic bottle. Do get yourself some bottles because we will be cutting up a whole bunch of them. And that's so the idea is you're going to press these to the bottle, but of course we need a valve to make sure that the air that goes in the balloon doesn't come out. So to make the valve, we will just use another balloon. So let's see if we can get a balloon and the cap of the bottle. So the cap is there, it has rolled off. So we make another hole in the cap, again with the scissor. There you go. Okay, a hole in the cap. Just use the scissor to ream it a bit and make the hole slightly bigger. So now you have a, can you show the thing? Yep, you have a hole. And look what's happening. We're, bring your hand a little in front. Yeah, we are stretching a balloon over this. We are stretching a balloon over this, nice and taut. And we're going to put a little bit of sellotape and okay, I could find the edge, but I'm holding the webcam. Okay, there we are. So we are just going to tape this around the edge. There we go. It's taped around the edge. Taped around the edge.
This forms a non-return valve.
Is your non-return valve. Essentially, when you blow from the inside, the rubber can stretch out, but the balloon air will not come out because that will sort of seal the little hole that we've made. So we've cut that tape, and just to make it a little neat, we will cut these edges of the balloon off as well. And the remainder of the sellotape around the thing. There's no audio on Facebook. Okay. Idea is you cover your thumbs, you use your thumbs to cover the two holes that we've made. Cover the two holes and you can press, and every time the little squeak tells you that air is coming out. So now we have to check if this works. So let's put a balloon on this and see if it's going to work. So there we've stretched a little balloon, and let's try our pump. There we go. One try, two try. Okay. So you get the idea? You get the idea. So it's rather easy. It's rather easy to make a pump with a old bottle that you don't need. Cut two holes, you press on them, air goes out. Make a little valve with another balloon and the cap. So that's in case you can't blow a balloon. This is one way you can think. If you can't tie a balloon, you can either put a rubber band around it or tie some string around it, or just twist it enough, and that should work. Okay, so let's assume you can do things. Folks, if you're on YouTube and Facebook, the only way you can communicate with us is through messages. So please do put your messages in the comments so that we can hear what it is. And I'm going to just take a minute to just check that things are working on Facebook and we don't have problems like last time with echoes and issues like that. So let me quickly check. Okay, let's hope. I'm just going to put a comment that please ask questions on the chat. I put that on YouTube, and let me quickly check if Facebook is it live? Yes, we are live. And let me check if the questions are there. It's a little tricky to try and do Facebook and YouTube from the same computer, and I'm hoping it's gonna not crash. Okay. Let's see if the comments say anything. I'm going very fast. Okay, I will try and go slow. That's what the comment is. And can you hear me? Someone, Haritara says you can't hear. Can you hear? Please, if you cannot hear, please put your comment on Facebook so we will know about it. And please put your questions here. I put a comment there, and let's get back to doing some experiments. Okay, so the first experiment we'd like to do is, of course, make a little rocket. Making rockets is easy, just with a balloon. Ah, you cut this balloon. This is what happens. This is what happens. Every time you set up something, Suryan uncle steals a balloon, and that's it. Okay, thankfully he's given me another one. Let me see if this one's going to work. Okay, you know what? I should check my zoom in here. Okay. So I've blown a balloon, and all I'm going to do with this balloon is leave it, and it just flew off somewhere. Now this is sort of a unguided rocket. What happened was there was air in the balloon. The moment I released it, the air came out of one end, and Newton's third law means that every action has an equal and opposite reaction. So the balloon goes in the other way. Now, unfortunately, unlike a rocket which is guided and goes up straight, our balloon had no guidance. It just went any way they like. Now, you could, of course, do a lot better. We can tie a string like that. It probably will. There's a heart-shaped balloon here. Let's see what happens to that. Let me get this balloon. Okay, here is a heart-shaped balloon. Today is International Friendship Day, and let us leave the balloon. It kind of spun around me. I think it likes me. It's a friendship balloon. It's a friendship balloon. Today's Happy Friendship Day. The first Sunday of India, first Sunday of August is Friendship Day in India, which is today. Internationally, I think it's July 30th, but anyway, Friendship Day. Happy Friendship Day, everybody. So yeah, the easiest way if you want to make a little bit more guided rocket is to, instead of just leaving the balloon, you can tie a piece of string somewhere from one end of your room to the other. And what you can do, we will need some, give me that, I'll show it to them. And then what you can do is, you can, if you want to make it really fancy, you can cut yourself a little rocket out of paper, get a little straw, okay, and stick it in the center. Yeah, you can stick it. Okay, this is, you can stick it in the center. You can stick it in this side also. It'll still work, right? And then pass a string through this. Pass a string through your thing, so it's guided along a string, and attach your balloon to this. That way, the balloon is forced to, it's pushing this along, and this will move along a string. But then for that, we need to put a string across this, and we are still trying to see how we can tie a string. But hopefully, we'll see what we can do. Okay, so now, before we do any other experiments, I'm going to try and show you the most difficult experiment, because I'd like you to think about this. I really want you to think about this. And this is a very famous experiment called the two balloon experiment. And the two balloon experiment, to do that, we've got Divya Shankar here. And Divya Shankar is going to try the two balloon experiment. Its experiment is very simple. You have a tube, and you have two balloons on either side, a big balloon and a small balloon. So let me just get to Divya. Let's get him. Okay, let's just make sure that he is visible. No, we've chopped off his head. One sec, this is not great. I will adjust it just a second. Okay, good enough. Okay, Divya Shankar, you're right there. Very good. Where are your balloons? Can you show us your balloons? So he's got two balloons.
Two balloons.
There is a green balloon and an orange balloon.
Oh, accidentally.
Which are connected by a tube. Of course, he has to blow it up. What he has done is he has tied the balloon with a rubber band on one end of a tube. If you're doing it at home and you don't have a tube, you can do it with a straw. With a straw, you have to be a little bit careful. You can tie it with, you can just tape it. You can take sellotape and tape a balloon to a straw, so you can blow it and blow into it from the other end. Okay. So first, let's just do the experiment. Maybe we'll look at the explanations in a bit.
Yeah.
So the first, Divya Shankar is going to blow one big balloon. Okay. Okay, and now we need to make sure the air doesn't go, so we just twist it. We just twist it so the air is going to remain in that. And we have a similar balloon from the same sort of packet, which we will blow not so big. Yeah, but a little bit, and he's going to connect it on the other side, and a little bit's going to leak out. Let it leak out. Let it leak out a little bit more. Yeah, a smaller balloon, so that's clearly one big and one small. And now, can you see that there are two balloons? The green is big, and the orange is small. Suren, can you show us your big balloon, because your hand is there it is. Now, let's suppose we connect these two balloons. What do you think is going to happen? Okay. Will the two balloons sort of exchange air so that they become equal size? Will the smaller balloon essentially get bigger and they become the equal size, or something else happens? So let's do the experiment. Let's see what happens. So we release the balloon. Let's release one balloon. It's connected. Okay. And this one is connected. And whoa, the smaller balloon got smaller and the bigger balloon got bigger. Let's repeat the experiment, because you should never believe an experiment done only once. Okay. So let's. Okay. So now we have two balloons. We're connecting them again.
The size of it?
Yeah, that's about fine. One is slightly smaller than the other. The orange is still slightly smaller. And okay. The balloons are connected. They've just pinched it with their hands. Okay. And he's releasing one balloon. The other balloon is released. Now, what's the size of the balloons?
The orange is smaller.
The orange shrinks. The bigger balloon increases in size. And this is very non-intuitive. Why should this happen? And just to show that you can do it with the straw, we will try and repeat this with a straw. There's a little trick in blowing the smaller balloon to ensure it doesn't leak, because getting the balloon leak tight on a straw at home might be difficult. So we'll just do this once more with a straw, just to show you. So on one side, what we've done is we've taken sellotape and really stuck the balloon to the straw over there. So you can blow it from the other side. Okay. Now you can blow the small balloon, and the way you make sure the air doesn't leak out when you do all this is just make a few twists in the balloon so the air will not leak out. Yeah, and that's the thing. You want to first put the balloon on your straw and then blow it. And remember, you don't want to blow very much, because you just need a small balloon. That looks good. And you have to pinch it and whoa. Now it leaked out. We'll try that again. You've got to be very quick in being able to put the sellotape around your balloon. Yeah, so there he is. Twisted it. And now at the mouth, we put some sellotape so that it doesn't leak out. Okay, and let's just show them that we have an unequal balloons before we release the air pressure in them. Okay, so now we have two balloons on a straw, and there is a big one and a small one, and we will now let them open it up. And what happens?
The left side balloon.
The left side, the balloon, the smaller balloon became smaller, the bigger balloon became bigger. They did not become equal in size. Okay, isn't that surprising? Isn't that surprising? So this is a very, very famous experiment. It's called the two balloon experiment. And we would like you to think about it. And at the end of the session, we'll give you the answer to really what happens in the two balloon experiment. It's not a very easy one to explain at all. So, okay, so that was a very serious experiment. Let's have some fun. That my rocket was sort of uncontrolled, but let's make a balloon spin, right? So yeah, we will get back to our one sec. We need the just hold this. We have a pile of books of the right height. You can show them how my stand is. So this is our great arrangement with some makeshift thing to make sure that these fat books are always useful. We use them to hold our camera in place, and hopefully what we will do on the table right now is we've taken a balloon. This is what we've done. We've got a balloon and we've got a little fruity straw, a bent straw. If you have a thicker, yeah, they actually forced me to drink the fruity as well, so that they could get a straw. And if you have the bigger bent straws, they are nice, but we didn't have any. And the only thing we could find lockdown time is a fruity straw. So we've sort of put a rubber band around it, made it tight. We have a balloon and we have a bent straw. It's important that you have a bent straw. And now we will blow the balloon up and let's see what happens. Let me quickly check if there are any messages. Okay, so
is the balloon seen properly?
1 minute. I need to check the. Okay, so can you see the balloon? It's probably a rather big balloon, but yeah, we should just get the white paper a little bit. Let's move our mess out of the way and put. We have some more posters. Can you just get me some? We will just
Tidy up.
Yeah, just tidy up the place a bit so you can see this thing better. Here's.
Get me one more.
One more poster.
That's it.
One more poster. Okay, so now we have a white table and a balloon which has got a little thing connected to it, and we're going to just leave it and let's see what happens. It's spinning, it's spinning, it's spinning up. So it's actually gone away from the table. Okay, so you saw what happened. This was like almost
Post done by the wall.
No, it's like a Diwali, one of those chakris,
Yeah,
Zameen chakris thing. The balloon was spinning. So why was the balloon spinning? Again, it's a matter of action and reaction, of course, but what makes it spin? So do think about it, and we will tell you the answer in a minute or so. Do think about it. So what makes the balloon spin? Shall we do this one more time? Maybe you don't blow it up so much to start with. Let's do this one more time in case people haven't seen it. We'll do it one more time. A balloon with a come on, autofocus. Okay. That's probably good enough. Yeah, that should be good. Okay, so here's our balloon with a little thing, and there it goes spinning. And as you can see, it's a little uncontrolled. It's a little uncontrolled, but there it was spinning. So why was it spinning? It was spinning because the air going round is actually sort of, put out in a tangential direction to the balloon, and the reaction makes the balloon turn. There's a sort of what is called a torque on it, and it will spin around. It's balanced. It's pivoted on the side of the balloon. Of course, our rubber band and the fruity straw, it's not a very sturdy connection, so it keeps flipping a bit, and hence it changes the direction in which it spins. Okay, let's spin some more stuff. Let's spin some more stuff. Let's make some noise. We got kids on the show. I think we need to. I'm sure all of us were naughty in school, and we made noise and things with this, and we spun stuff. So let's do one thing. Let's if you're doing this at home, take a balloon and put a coin in it. Okay. So
I'll show you.
yeah. So let's just do it here so that people can see it. Yeah. So there is a coin. A coin. Yep. That you put inside a balloon. So you put the coin inside the balloon and then blow it up. Okay. So blow the balloon. I think I know how to catch the camera. Yes. Just wait. I need to see this. I'm going to keep it here. Okay. So can you see that there's a coin inside it? You could probably hear the coin jiggling. Let's just make sure. Let's tie it properly. It's fine. We'll let you tie it. Unfortunately, we don't have transparent balloons. This actually works nicely if you have a transparent balloon. Can you see the coin? Yeah, there's a coin. Okay, now we're going to turn the balloon and make the coin spin. Okay, wait. Hold it in one place. Ah, that's good. Can you see the coin spinning in the balloon? Now notice, even when the balloon is turned, the coin keeps spinning in the same axis. Okay, let's spin this coin again. It requires a bit before the coin starts spinning on its edge. Yeah, once it does, it spins pretty quickly. Okay, now you hold it and you can see the coin spinning. Now tilt the balloon and it still continues spinning the same way. See, the tilt of the coin doesn't change. The plane in which the coin is spinning doesn't change. Eventually it will fall down. Okay. So this is again a beautiful example of things in motion in a circle where there is something called a centripetal force and a centrifugal force, depending on how you look at the problem. And it keeps the thing spinning, and something which is spinning does not like to change its direction. This is again something called conservation of angular momentum. And even if we tilt the balloon, the coin keeps spinning in the same plane that it was spinning in. Okay, but of course the coin spinning, we had this balloon with the coin spinning in it. It made a little bit of noise. It made a little bit of noise initially when the coin was jiggling around, but once the coin starts spinning, it's not really noisy. Now, if you really want to make a pest of yourself and annoy your neighbors or something, this is a good thing to do. Instead of a coin, take a nut,
Hex nut.
a hex nut. Okay, something which is six-sided, and you put a hex nut inside the balloon, and you do the same thing. You blow the balloon up. Actually, can you lift these boards up? I think the green background will be better.
Yeah.
And now when you do this, it's going to make really Did you hear this buzzing sound?
Ring of death.
Okay, let's do this again. And when it stops, you can even generate some music with it because the frequency will change depending on how fast you spin. Okay, I think they get the idea. Okay, all right. I hope you like that. So if you really want to irritate your neighbors, you know what to do. Put a little hex nut inside a balloon and
the corridor.
Go around the corridor, and I'm sure you'll have lots of people coming out to figure out what's happening. Actually, you know what? We can make more noise. There are lots of interesting ways you can make noise with a balloon, and one of them is
diaphragm. Show them the diaphragm.
Yeah, so we'll make it from scratch.
We'll make it from scratch.
Okay, so we'll just take this out and we'll make it from scratch.
Okay.
Okay, so what we'll do is we'll show you how to make a little bugle, or it's a vuvuzela or a bugle or whatever you want. What? Yeah. So it's okay. So he's going to take a balloon and cut a bit of it.
Small
Can you just draw on the board what you cut out? Just draw a schematic on the board so we know what you're doing. So that was your balloon. You just cut out a little arc from it over there. Okay. Can you just make that a little dark? The part that you cut out? Yeah. So that's what we are cutting out of the balloon. Okay. So you made a little, you've cut a circle out of the balloon in a way, approximately. Okay, that's fine. That's fine. I think that's good enough. And then we are going to put a bottle cap, a mouth of a bottle, sorry, remove the cap from the bottle and put a bottle into it. Of course, we have cut it's only the top of the bottle. So that's what we will do right now. We've taken a bottle.
We have a funnel
and we've cut the. So it's just a bottle which has been cut. And we're going to use the top half of it, or not half, the top little bit of it. This is just a little funnel type thing, and this is going to be effectively our loudspeaker, our horn, And we are just going to put the part that we had cut over the mouth of the bottle, over the smaller end, the place where the cap goes, and we stretch it. Make sure that you stretch the rubber over here. Over it, and again, to keep it in place, you need a rubber band. So we take a rubber band and make sure that it's pretty taut. So multiple times you crisscross a rubber band over it, and now what you have is a bottle cap which has a sort of film of rubber over it. Okay, and remember that the place where you would have normally blown into the balloon to inflate it, make sure that is above the rubber band, and that's visible. I mean, that you need to blow through it, right? So yeah, just make sure. We'll show them, just tie it up and then we'll show them what exactly. Yeah. So okay. Okay, so now you see that the part that is where you blow on the balloon is loose, but the rest of the balloon is sort of a little thin, taut film around the mouth of the bottle. And the next thing you need is a card. Wait,
you have that, but then
no, I'll do it. Just hold this. Just hold it on the table. Or hold it. There is so you need a postcard or something like this. You need a little postcard. Okay, here is my postcard. All I'm going to do with the postcard is roll it up. Yeah, just put it on the show it on the ground. Yeah. So I'm going to take this thing and just roll it up into a firm tube. Okay, I've made a little tube, and to make the tube firm, you just put a little sellotape around it so that it doesn't come out. We're not doing it here, so. Yeah, we put some sellotape. Go all the way around. You don't want an air leak in it either. And
yeah, use this.
Okay.
Takes about less than a minute to do this.
So it takes about a minute to
do all this.
Put the
tape around it.
Tape around.
Make sure that there is no leak from the.
So you want to really go around it very well, because you don't want air to leak from the side where we,
blow on it.
The edges are open, because we want to blow through this. Okay, that looks good. We chop it off. And now you've got your tube to blow through. And we will just connect it to our, if you have a small piece of pipe, that will work as well. But otherwise, you can just fold
roll a cardboard.
roll a postcard or something and make this tube. And almost there, you thread it.
If your
you
balloon
sort of
is
put
too
your
large,
balloon.
then you can put a rubber band to make it airtight.
Okay, you can then push this tube through.
Yeah, it's ready. You can do it.
Okay, do it. I'm holding the camera, so you can do it. And all you need to do is, there's a leak somewhere, so you fix it. Yeah. Okay. So you just got to blow through the tube, and that makes this little rubber diaphragm that we've stretched over the mouth of the bottle vibrate, and it generates a little, again, a buzzy noise. Let's try that again. You have to play with it to get it right. I mean, in all these things, it's kind of difficult to do it when you're trying to do it in front of a camera and people watching, but it generally, you play with it and it works. Let's try that again. No, not yet.
Okay, let's do it.
Okay, we'll fix that. And while we fix that, let's look at some other cool experiment. Shall we look at the two balloons which we have stretched over here?
Yeah.
So maybe I can just hold this. I'll show them what this experiment is about. Okay, so you can see that we have two balloons which are hanging from a rod over here. Okay, there are two balloons hanging from a rod, and okay, I should be very careful. The idea was to keep them hanging. We hung them before the thing so they would be steady. And what do you think is going to happen when I blow air in between the balloons? Suppose I blow air in between the balloons. I'm going to go to the other side and blow air in between the balloons. I guess I should move the screen a bit back so I can squeeze in here and blow air in between the balloons. So I'm going to try and blow air in between the balloons, and let's see what happens. The balloons came together. Okay, let's try this again. The balloons come together. So who's pushing the balloons from the side? See that? Every time I blow air, okay, now the balloons are going to bounce around a bit, so we can't keep doing it. But if you blow air in between the balloons come together. Why does this happen? This is an example of the Bernoulli effect or whatever else. If the flow is fast, the pressure is low. And this is the same thing about airplane wings, etc. You have a higher speed air on top, lower speed air at the bottom. So if the speed is high, the pressure is low. So the pressure in between the balloons is lower than the outside, and hence the air outside sort of pushes the balloons and they try to come together. So these two balloons hanging make for a very simple demonstration of the Bernoulli effect as well. Okay. Talking about thing, is your thing tooting as well or not yet?
It will toot.
It will toot. Okay, we will see that he makes his thing toot. Meanwhile, okay, do you want to try that? Otherwise, we can go to our next experiment with the. Okay, let's see. He thinks he can get it.
If it doesn't, by the end of before the end of the show, I'll show it works.
You got to beat this in sound. The idea is you've got to be really careful in putting the balloon onto the tube where you will blow, because you don't want it has to be a tight thing, but you should be able to blow through it as well. Nope, not yet. No, I think we'll do it. We'll just try and set it, because you can make out this thing as ballooned up over here. So it's okay. Definitely got a leak. Let's try the diver.
Yeah.
Okay, we'll do yet another experiment. So here is a bottle of water. Let's clear this out so we have a reasonable. I don't have some kachra in the background. So we just want to focus on the bottle of water. Get it down. Let them see the side view. And in the bottle of water, there is a okay, there's a bottle of water. And what we've done is, I don't know if you can show this very clearly, but just to make sure that the balloon floats or sort of vertically, we have put a gem clip. Can you see the clip at the bottom? So there is a gem clip just to weight the balloon down. So it will remain vertical. We haven't blown up the balloon. There's always a little bit of air trapped in the balloon. That's good enough. Okay. So the balloon is in water and it is floating at the top. And I will tightly close the lid on top. And now what happens when I press the bottle? If I press the bottle, nothing happens.
Just a minute. Just a minute.
Wait, you have to really.
No, that's it.
Did you see it went down? Okay. You release the pressure, it comes up. Press the bottle hard. Our little diver went down. Release the bottle. The diver comes up. What is the diver? It's just a balloon with two gem clip attached to it at the bottom so that it will remain vertical. Now let's figure out why this happens. So this is an experiment in why is something buoyant? Why does something float? Clearly it is floating initially because there is air in it, and overall the density is lighter than water, so it is sort of at the surface a little bit. It's almost like an iceberg. Most of it is down, just a little bit on top. But now if I really squeeze the bottle, it goes down, and by playing with the pressure on the bottle, I can actually control. I can hold it in the middle, make it go down, make it go up. Okay, so what am I doing by pressing the bottle? So by pressing the bottle, and do note that you have to put a weight on this. So you got the two gem clips over here. Do you see the gem clip? You need the clip to weight it down, but all you have trapped, I can hear him. There he comes. Okay, this is how you irritate people. Okay, that's not quite a bugle, but you'll agree it's irritating. So let's just focus on that. It went off again. So you get it at times. So the idea is you have to make it stretched and think, okay, let me come back to our diver. Let me come back to the diver. Come on, diver. The diver does not like to face the camera even if I rotate the bottle. Okay, if the diver doesn't face the camera, we'll turn the camera back. And there, you really have to press the bottle quite hard. If you press the bottle, the guy will go down. Release the pressure, comes up. Now, the thing with water or any fluid is if you press it, whatever pressure you apply, remember that the bottle is sealed, right? The bottle is closed on top, and that I should have mentioned that you must close the bottle on top. Okay, so once I press the bottle, the pressure inside, I'm applying the pressure on the water. The water is pressing everything equally from all sides, including the balloon, including the air on the balloon. And once the air gets, now the water doesn't get compressed very much. It's very difficult to compress water, but it's very easy to compress a gas. So if you compress the air, it occupies slightly smaller volume. So the same amount of air in slightly smaller volume means that its density has now gone up. It's going to be slightly heavier than what it was before. The density is higher, heavier per unit volume, and it starts to sink. Once I release the pressure, it floats up again. So what I'm doing, my thing is, I'm actually compressing the air, the little bit of air that's trapped on top of the balloon. That is what we are compressing. And as we compress that, the density of the air changes, and I can make this go up or down. Now, if you're doing this at home, you will have to play with it and see that if you trap too much air, even if you compress it, it'll still float. If there's too little air, it'll just sink. So you have to play with it till it just sort of floats over here. It just floats. Okay, this is about what you want if you want to do this experiment. Okay, so I hope you are enjoying these experiments and are able to follow along at home with at least some of them. Let me just take a quick check at questions if there are any coming in. If there are questions coming in on YouTube or on, I don't have Facebook here. You're watching Facebook. Okay, somebody's watching Facebook. Okay, good. So no real questions so far. So okay, so we are doing that. We've done the diver. So remember what we did in the diver was we were looking at the air being compressed over here. Now, when you compress air, its pressure changes, its volume changes, etc. And you must have heard about changes in pressure and volume. And okay, hopefully, if you've been in either high school or college or whatever, there is one law that I am sure you must have come across, and people must have told you about Boyle's law. Boyle's law, the relationship between pressure and volume. It comes in many forms. You can say that pressure times volume is a constant, or typically they will say something like P1 V1 is equal to P2 V2. Now, how do you see Boyle's law in practice? Now, remember the changes in the volume of that balloon in the water was not visible, but we can show you Boyle's law in this is a demonstration that you probably won't be able to do at home because you need a rather large syringe for it. So let me just keep the. I'll just hold the camera. Just wait. I need to look at my. Okay, just hang on. So first, let's tell them what we have. Move your hand. So we have a very large syringe, 50 ml. A 50 ml syringe. A 50 ml syringe, which has a tiny balloon inside it. And Suren, how did you blow this tiny balloon?
Guti banaya.
So how do you do that? Can you just show people how to make a tiny balloon? If you want to make a very tiny balloon, it's very difficult to blow into it. Okay. So if you blow into it, you will get a balloon which is that big.
So you need to read.
Okay. You really need to make a very small balloon. And to make a very small balloon, what you need is that you want to make a tiny balloon which is going to fit inside a syringe. But that's going to be really, it's not easy, especially if you're starting off with a big piece of a rubber balloon like this. So the trick to making a small balloon is to trap a very little bit of air in the tip of the balloon like this. Okay, there you have a little marble-like balloon. That's the little marble of a balloon that you want, and then you use a rubber band or something to really put it in place. Okay, so we've done that, and that's the way you. That's the way we make a balloon, a tiny little balloon. Okay, remember the balloon must be such that it fits into a syringe. There you go. Oops, that's okay. The rubber band tore off, but the knot is still there. And you can even cut off the rubber at the bottom if you want the extra balloon at the bottom. So you get a little marble-shaped, a marble-sized, teeny little balloon. And this teeny little balloon is what goes inside a syringe. And once you have a balloon inside a syringe, I'm going to look at the top view probably of this. Okay, now look at the size of the balloon. Wait, let me just make sure that I'm centered. Keep your hands in one. Yeah, okay, that's good. Yeah, keep it there. Okay, now remember that as of now, the thing is open. So there's the same air pressure on both sides. Same air pressure on both sides. Do we need more light here?
If possible, yes.
Yeah, we need some more light here. It's a black balloon. That's just giving us more reflections from the paper. No, that's just giving us reflections. Okay,
I'll change the color.
Let's change the color of the balloon. That way it would be easier for you to see. Identify. Okay, so we just cut off this contraption. cut off a little marble. Those.
Should not give away in the
Okay, so we just try and change the color. So you see the, use a pencil or something to get that. So we get that old one out. Nice. Yeah. Okay.
No, this is
So
really
there, yeah. So we have a little balloon inside the thing, and now where is the? Okay. Now see the size of the balloon. Now we're going to put a finger out here to shut the thing, and watch what happens when we compress it. You see the balloon becomes smaller in size. Maybe if you take it out, you'll see the balloon expand. There it expands again. That is atmospheric pressure. Now what we will do is, now it's atmospheric pressure, we will reduce the pressure. We will shut the front and pull the syringe back. And did you see the volume of the balloon increases? Right? So the lower the pressure, the higher the volume. So pressure multiplied by volume is a constant. So lower the pressure, higher the volume. If we increase the pressure, the volume becomes small. Okay, and this is an example of Boyle's law, which you rarely ever see an experiment in a lab, but it's actually very easy to demonstrate with a balloon and a syringe. Of course, your finger is going to hurt after a bit because you will be really compressing it. And there you see how small this marble has become.
okay. Drop in now.
Yeah, it can be much smaller than if you, yeah. So there it is. And if you pull on it, we can increase the size of it. See this. If we decrease, so there we are. Now it's at atmospheric pressure because it's open. You shut it and you reduce the pressure, and you can see that the balloon expands. So pressure into volume is a constant. This is Boyle's law, a very simple demonstration with a syringe. Okay, so all this while we've had Boyle's law, etc. Let me just put this camera back so I can see you all. Okay, I hope Sunil is ready. Okay, so Boyle's law, all this, where are these balloons used? Let's take you to the balloon facility in Hyderabad that TIFR has. And these are not just tiny balloons, but massive balloons. So with me is Sunil Kumar, but we need to be able to hear him. So I need to connect a speaker. So can you just give me that? We just connect a speaker because my laptop speakers may be very, very soft and we won't hear him. So Sunil Kumar, are you there? Yes, he's there. He is unmuted as well. I will pin his video so we can see him. And yeah, so this and mute that. And I just need to make sure speakers are chosen correctly. Just a second. Okay, I think we use the micro. Okay, Sunil, are you there? Can you hear us?
Yeah.
Wait, you went mute. Just go to your max volume there. I'll set it from here as well. Okay, so with me is B. Sunil Kumar. the scientist in charge of the TIFR Hyderabad balloon facility, which is a absolutely unique facility in India. Now my computer finally recognizes the device. That's how fast it was. Okay, sorry for the delay. Thank you so much, Sunil, for joining us on a Sunday from home. And you guys do some very fantastic work on these balloons. So first thing, how high do our balloons go and how big are they?
Our world record is 54 kilometers. That was done by Japan, and we reached 51.8 kilometer maximum altitude, which was called the mesospheric balloon. For all atmospheric science balloons, they go up to 18 kilometers. Our TIFR astronomy experiments, they go from 30 kilometers to 43 kilometers.
Wow, wow. I mean, just imagine this. This is what happened? Okay, so basically, you know, planes fly. Mount Everest is like 9 kilometers or something. Planes fly at what is it? 10 to 12 kilometers perhaps, and planes fly 10 to 12 kilometers. These balloons you're saying are 30 kilometers to 40 kilometers, and the world record, I mean, our record is some almost 50 plus kilometers.
Yeah, yeah.
That's nearly the edge of space, right? And why do we, you know, why do we go up to those heights? What are we studying?
For these astronomy experiments, they want a stable platform to study about the stars. So that's why we are sending the balloon. It's a slow-moving balloon, like 3 to 5 meters per second, and which goes up to 32 kilometers and stay at the same altitude for several hours, which is not possible using the satellites or rockets. They are very fast-moving things, and even with aircraft also we cannot do it. So that's why the balloon is like a cheap and reusable thing. So we recover the instrument, and we can reuse the instrument for conducting several experiments.
And how big are these balloons?
These are like maximum balloon is the diameter is around 150 meters in horizontal and 170 meters in vertical.
Okay, I don't know if 150 meters and 170 meters means anything. Just remember that a 100-meter track in a stadium is 100 meters. And a stadium is typically, you know, 10-20 meters on each side. So the balloon is bigger than an Olympic-sized stadium. Just imagine your Wankhede Stadium or something. The balloon is bigger than Wankhede Stadium. The whole stadium will fit inside the balloon.
Yes.
That's how big these balloons are. These are massive balloons, massive. But,
yes,
you know, they don't look that big when we launch them. You sent me a launch video, which I will show after we've spoken. It doesn't seem very big, right? The balloon just seems hardly 10-20 meters when you launch it. And you're saying it's 120 meters, 150 meters.
Yeah, as simple like whatever you mentioned in the Boyle's law, that pressure volume P1 V1 at the ground, and if you keep on going up, the pressure keep on decreasing. Let us suppose our X-ray astronomy experiment. The pressure at that 42 kilometers altitude was 2 millibar, and the pressure at surface level at Hyderabad was 950 millibar. So accordingly, we have to inflate the balloon almost like 1/30th part of the full volume, say around 20 meters or 25 meters in the ground, then which goes up to 40 kilometers or 42 kilometers. Because of the pressure, the gas inside the balloon expands and it occupies the full volume of 4 lakh cubic meters. Whatever we are inflating around 2000 cubic meters was expanded to 4 lakh cubic meters.
Wow. Wow. That is, see, so Boyle's law, this P1 V1 that we keep talking, which we showed you a very simple demonstration with a syringe over here, is actually very important when we do these high altitude experiments. The pressure out there is probably 300 times smaller than the pressure on the ground. So we have to be very careful, because if we filled the balloon on the ground, it would just go there, expand and burst. So to do that, the balloons are actually not filled completely. They're filled only partially, and they go up, and with height, they will expand and then, provide something. But such a big balloon, I mean, what if a bird hits it? Have you ever? It's very thin, right? I mean, these are these rubber balloons, or are they like balloons like this, or there's some different material?
So that is actually, we use linear low density polyethylene material, even though it's a plastic which is having 1000% elongation at room temperature. And also, so far, nothing happened with the birds because our balloon moves, it's a huge object, moves with a 3 meters per second ascent rate. The birds definitely they will afraid to come and hit the balloon. And also, it's a reflective material. The balloon will reflect. The birds will not come and dare to come and hit the balloons.
So okay, no bird hits, and also I think birds are not flying that high anyway, right?
Only thing is the eagles, they are little there, but even the balloon moves slowly, it generates a huge noise with the friction of air. So even eagles also don't dare to come near to the balloon.
Okay, so where eagles don't dare, that's going to be our next TIFR Hyderabad movie, I guess. And do you need permission from the? Do you have to worry about planes flying, and do you need to coordinate with the airport or something, or how do you do this?
Yes, yes, definitely. See, any balloon if we would launch, so we need to take prior permission. 15 days prior, we have to intimate to the all airports. Comes under Airport Authority of India, which are 66 airports around Hyderabad. We intimate to all of them, and we obtain the permission from Samshabad Airport ATC. So, and also we are using a transponder, which is the secondary surveillance radar. So that is our balloon will be shown on their radars during the launch time.
And I mean, you have no control where the balloon goes, right? After it goes up. So, I mean, how do you go and recover your equipment?
We use the S-band tracking system and also onboard GPS. The GPS gives the altitude, latitude, longitude continuously. So our people from the beginning, from the launch, our people follows the balloon, and balloon moves according to the prevailing winds. Mostly it will be from east to west we prefer, and we have 400 kilometers corridor in the west. So that is approved by DGCA, Government of India. So our people follow the balloon, and once the experiment is over, we give the radio commands from the ground station to terminate the balloon flight, which separates the balloon from the payload. So payload safely comes using the parachute, and once it touchdowns, our people go and recover the payload, not the balloon.
Okay, and you can reach there fast enough because your balloon is traveling with whatever wind is going there, but your people are traveling with Indian traffic, right?
Definitely, we will prefer the low altitude winds, maximum 10 meters to 15 meters per second. And anyway, so far our people are reaching within 1 hour and recovering the payload as it is.
And what is this I hear about sometimes? I mean, the villagers will keep the balloon, and you have to give them some, incentives to get your thing back.
No, for that we do some administrative job. We send the request to the district administrators about the balloon information. They will announce in the villages where the probable landing will be there. The villagers also are well known about this balloon launch. And also we are keeping some reward labels. Those who find the payload, they can inform us, and we are giving a nominal reward amount to them. And
Wow.
also we intimate to the local, we take the local police help also. Sometimes they will go and report to the police, then police will safeguard our instrument and they will inform us for collection.
Very nice, very nice. And what is, I believe some of our TIFR balloons have been used to set some really world record kind of, for some, not
Yes.
just for science, but for some other fun experiments as well, right?
So these are all used for the human flights, where in 2015, from Paragon Space Development Corporation, USA, they conducted a flight with a human inside the payload. So they went up to 41.4 kilometers, and he jumped from there, terminating from the balloon, and he jumped and he generated 3 records, and he safely landed on the surface. And also last year, 2019, Julian Knott, he conducted human flight and he went up to 8 kilometers and flown for 26 hours at the same altitude.
So
And also
TIFR balloons are creating world records.
yes, yes.
Fantastic, fantastic, Sunil Kumar. Thank you so much. And he has actually sent us some videos of balloon launches, and these balloon launches are just they are beautiful to watch. It's so different than a rocket launch. You must have seen videos of ISRO launching rockets. I mean, which is also fantastic. I mean, rockets are all about power, about, you know, there's a huge thundering noise and things just take off and whoosh, it goes into space. A balloon launch is gentle. It's beautiful. I mean, you have to watch it. And we have some very nice videos both of the launch as well as a video from the balloon at 36 kilometers when it's getting separated. So thanks a lot, Sunil, for joining us. And we will surely have a Chai and Wai from Hyderabad during a balloon launch. We will try and cover a balloon launch live because it's something really worth watching. We should go to Hyderabad and do it. By the way, do you launch balloons in the monsoon as well?
Yes, sir. Yeah.
I mean, not COVID time, but you know, otherwise.
So this is actually for collecting the air samples from 18 kilometers, coldest tropopause region, for studying about the cirrus clouds, which is from 11 kilometers to 18 kilometers. And we collaborated with NASA and ISRO for conducting these balloon flights. Last 5 years, we conducted the balloon launches. This year, unfortunately, we have not conducted.
And it must be, you said tropopause, so it must be very, very cold, right? The balloon has also got to go through some very big temperature gradients as well, right?
Yes, sir.
I mean,
it's observed.
If I had a rubber balloon, it would just crack.
Yes, yes. Our material is having a cold brittle point of minus 90 degrees centigrade. Even it is a plastic which is having elastic properties at that minus 80 degrees centigrade. Even what our lab test conducted, it is having around 200% elongation at minus 80 degrees centigrade.
Okay, great. I mean, this is just so interesting. You know, remember that there is so much of a difference between making a balloon like this, which is typically a rubber balloon, versus these very specialized balloons, which are only about 20 microns thin. I mean, remember the plastic bag that you're allowed is 50 microns. You have a balloon with you in your hand somewhere?
Yes, yeah. This is the simple plastic material.
Wow.
So which is having 1000% elongation. And that too, this is 2-layered. It's a 40 microns film.
Oh, it's a double
layer.
That's only 20 microns, and it's
yes.
strong enough that it can go all the way up to 30-40 kilometers, no problem. But the balloon itself must be quite heavy, right?
Balloon in general, it is like 500 kgs for carrying 1000 kg payload. But
wow.
The balloon material will not take the load. A special material called load tape that will be taken the payload. It is only as an envelope to hold the hydrogen gas.
Oh, you use hydrogen gas, not helium.
Yes.
Like most common balloons use helium, but you use hydrogen.
Yes, yeah. Helium is rarely available and it is very costly. And hydrogen is easily available, and we are taking the proper precautions to use the hydrogen.
And it also gives you much more lifting power, I guess, compared to helium.
Yes, yeah, definitely hydrogen gives the much more lifting power than helium.
Okay. Yeah, we will definitely have a Chai and Wai on balloons from Hyderabad. But for now, thank you so much for joining us. Thank you for your time on a Sunday. And let's get back to the Chai and Wai. Thanks a lot. I hope, audience, you enjoyed this little conversation with Sunil Kumar, the scientist in charge of the TIFR Balloon Facility. Okay, so I'm going to try and see if I can find a video to show. But a reminder that we wanted you to think about the two balloon experiment. And the two balloon experiment was something which now the balloons have got deflated. But we had one big balloon and one, I think I should pin my video. Yeah. So we had two balloons. One was a big balloon, one was a small balloon. And when we connected the two, the big balloon got bigger, the small balloon got smaller. This was a 2-balloon experiment, and we had told you that we will explain why this happens at the end. Meanwhile, just give me a minute because I have to find the file that was sent, and let me just do that real quick. Okay. Can you keep all speakers off? Okay, so while I try and download this video, first thing to remember for the 2-balloon experiment, which is very, very standard when you blow any balloon, is if you've, Suryan uncle, can I get a balloon which is not yet cut open? Every balloon I seem to find is something which has been cut open. There we go. Okay, so if I have a balloon, and if you try to blow a balloon, initially it's very hard to blow. The first part of blowing a balloon is hard to blow, and it gets easier once it goes beyond a certain size. So initially it's very hard to blow. I even missed it. So till somewhere of this size, it's hard to blow the balloon. Now, once I blow more, the second part was much easier than the first part. Okay, so the balloon is initially difficult to blow, and then it becomes easier to blow. And this is a very key thing in when we discuss the 2-balloon experiment. Okay, I have found this, and I will have to download the file again because I'm doing it from my tablet. Okay, so let me try and explain what's happening. So what is happening effectively is, finally, it's going to be a difference in pressure that makes air flow from one balloon to the other. Okay, and air is going to flow from something at a higher pressure to something at a lower pressure. And now, Suren, if you can just point to the board because I need to draw something. So I'm just going to draw on the board. You will have to look at the screen here. Okay, so let us suppose this is the size of the balloon, and this is the pressure inside the balloon. Okay, and remember the fact that initially it is hard to blow because initially the pressure sort of rises rather quickly, and then actually the pressure starts falling. Okay, and now if I start, so this is size. If I start with a large balloon which is somewhere here, and a small balloon which is somewhere here, what's going to happen is, instead of the air, sort of flowing and making this balloon larger, if both balloons have to become the same size, this balloon would have to become larger. But what happens is, finally the pressure on both will be the same. So this the larger balloon actually becomes larger. It goes somewhere here, and the smaller balloon sort of comes down here in size. So the smaller balloon shrinks and the larger balloon gets larger because of the way the sizes and the pressures are. So a small size balloon, actually, it's favorable for this guy to shrink and go down. The large size balloon expands. And it's a lot more complex in real life because The rubber of a balloon is an elastic material. It's not an ideal material. So and this elasticity this is what is actually leading to all of this. Do look at the Wikipedia page for two balloon experiment, or there are lots and lots and lots of sites that explain this two balloon experiment, and it's actually very important. I mean, the two balloon experiment, it's a toy demonstration done in physics, of course, but recently for the COVID-19 crisis, they were wondering about whether people could share ventilators. And ventilators are things which are going to blow air into lungs, and lungs are nothing but balloons, right? And remember that if you have this two balloon configuration, the weaker lung will actually shrink, the larger lung will get something. That's not what you want to happen. And this is why it makes sharing ventilators very difficult to share ventilators between patients. Otherwise, you could use one ventilator for two patients perhaps, is because of things like this, that you have to worry about how these balloons behave when they are filled, and depending on the elasticity, etc., etc. So this is actually something which is not very easy at all. Okay, but this is the simplest way to explain it. A balloon initially is hard to blow. So if you have something which is here, it's going to come down. Once you blow it, it's much easier. So this is pressure versus size, and it's actually a rather complex thing that happens. Okay, so let's see if we've got the video downloaded, and if that is done, we can try and show you the video. Yes, we have, and let's see if I can use VLC or something to open this. Open with VLC. Yeah, I'm going to do a share screen, but oh wait, why is it doing this? Why is it doing this? It's not even. Too many things open. Let me just double click and see what it plays in. Okay, that should be fine. Share screen. Share screen. Okay, so don't worry about sound. There isn't much sound in this video. And this is a video of one of these sort of relatively big balloon launches with almost a 1 ton worth of equipment that's going to go up. The equipment is actually sitting on a truck in the sort of left side. You can barely see the lights. You see lots of balloons on a string, and many of them are just test balloons to figure out where the wind is going. At the beginning, you'll see a very small balloon going up. That's just a balloon to test again the wind. And it's about a 90-second video, so let's just watch it. Is it playing? No, it's not. It's sort of frozen. Wait. Oh, it's very jerky. I think it's my RAM issue trying to work too many things. Wait, let's close applications.
It's not going through.
It's not going through. The video is not going through.
It's very patchy.
It's very patchy.
What we can do is we can upload it on the YouTube channel later on.
Yeah. Okay, so what we'll do is we will just upload the video on YouTube, I think. You can watch it. Let me just get back to the Zoom call and try and finish it. We're almost out of time here. Yeah, it's unfortunately a massive ½ gigabyte video, so it's having difficulty on my laptop. It's not even. I'm going to stop this share. My screen is frozen as well. Okay, sorry about that. It almost the video sort of slowed down my computer to a point where nothing was working on it, even freezing Zoom. So I think what we will do is we will put the video on YouTube. We'll share the YouTube link. Do watch the video. It's only 90 seconds, but it's just beautiful to watch a balloon launch. And hopefully we'll bring you one of these launches live one of these days. After COVID and whenever they resume the launches, we will check if we can go to Hyderabad and do something. Meanwhile, I'm sure you have questions. So if you have questions, Divya Shankar, can you please check the Facebook or YouTube channels to see if there are questions coming in, and I will try and answer some of the questions over here.
Why do we need holes on the balloon?
On the
bottle.
Okay.
And as well as balloon as a.
Okay. So the pump. This very simple pump that we had made. Let me try and. So how does a pump work? A pump works by taking a fixed amount of air, blowing it into the balloon, and make sure it can't come back. Okay, so that's what you want. You want to be able to somehow have a one-way valve where things can only enter. So how is our one-way valve designed? Let's take a look at the one-way valve. So this is the one-way valve. You have a bottle cap which has a balloon stretched across it. Now, if I blow from inside, the balloon, this thing, the air will press this rubber piece. It will press this rubber piece, and on the outside, the air can escape from the sides over here. So if I have a balloon, it will get inflated because air from this side. So if I now shut this, I have this. If I press this, this volume has gone down, so that air is expelled through this. It can go inside, and it can't come back because this rubber gasket will seal against the balloon. Okay. Now the question is, why do you need these? Now, I don't want to do this only once. If I did this only once, the bottle would just get crushed. It would not open up again. Now, I wanted that the air has to enter this. The air from the room has to enter this. And for that, we made these two little holes. You could have made one hole, but since we have typically two hands, it helps to make two holes. So you can go press, press, press. And if I mount a balloon, I'll just do this one more time. Let's stretch a balloon over the mouth of this. Oops, can you just do this? We can stretch a balloon across it, and then it will try and do it. Okay, what other questions are there?
Can't we use not balloons and clothes or something?
Can you use cloth? Well, cloth is porous. It will allow the air to leak out. So okay, so here is what we've done. You can for the pump, you put a balloon on this, and then you have, this is your reservoir of air. So if I press this, the air goes inside the balloon, and when the bottle comes back, room air gets into the bottle. I press this again, one more shot of air goes in. I press this again, one more shot of air. So it's not very efficient because this bottle doesn't hold much, and it's an old bottle, so it creaks a bit. But I can use this to sort of inflate a balloon. Again, if you have a little bigger bottle or a little sturdier bottle, it would probably help. Okay. The question was, why can't you use cloth? Well, in general, cloth is porous and would not hold the air. You need something like rubber or plastic or something which holds will not allow the air to go out. Yeah. What are the questions?
How does the deep sea driver control the jet he will go in? As he goes deeper, pressure will increase.
How does a deep sea diver control the depth you go in? Well, you just saw this example of, if I have a volume of air, by compressing that air, I can sort of control my overall density. So obviously, a deep sea diver has packs of air, cylinders of air. If you release that air into a larger area, you can sort of inflate something and make yourself lighter and go in. And obviously, with all that weight, those cylinders are almost 30 kilos outside. There'll be some reduction because of the density of water. It's not air, you're in water. But still, that weight will make the person sink. When you want to come up, you have to sort of increase your buoyancy, and that you can do by letting in air and somehow inflating it. But the idea is the same. You have to control your density by changing the volume, the pressure and the volume of a region of gas. Other questions? Anything on Facebook?
Does India have all the technology to produce a balloon, or we have to buy all the
No, in fact, what Sunil Kumar just told us is that India makes the balloons for most of the world, requiring these very, very high precision manufacture of large balloons for high altitude, either experiments. So the balloon facility, to the best of my knowledge, has collaborated with NASA, with the Singapore Science Agency, etc., for these high altitude experiments. Of course, with ISRO, etc., and even for sort of adventure sports, when they wanted to have this stratospheric jump, the balloon actually was made in TIFR. Very few places in the world can make these balloons which can go up to 40-50 kilometer height. So we have everything in-house in the TIFR balloon facility to make these balloons.
Are those ropes strong enough to possibly take the balloon to the ground? What is the limiting factor?
Okay, so remember that the load is not hanging from, okay, it's not this balloon in the first place, but the balloon actually has some tapes on the sides. These are what are called the load tapes. And the load is connected to those tapes. And those tapes will take about, maybe 60-70 kilos each. And there are many of them. So you can hold your 1 ton weight or whatever you need to take up. In that, the balloon is just lifting everything up together. And the tether wires are only used when it's on the ground, and they can definitely, wires and cables are very strong. They can take all the thing.
How much does one balloon weigh, considering the mass?
How much does a balloon weigh? So the biggest balloons, the balloons which were like what I call the Wankhede Stadium balloons, which are 150 meters across and 170 meters tall, the balloon itself weighs 600 kilos. The balloon weighs 600 kilos. It's filled with hydrogen gas, and it can lift 1 ton. It can lift 1,000 kilos. Which is a very different thing from your little party helium balloons, which will go and, they might get to the 10th floor or 20th or something of that sort. Okay.
Can you explain how the trumpet works?
Can I explain how the trumpet works, or the trumpet which wasn't working very well works? Let's try. So here is the trumpet as such. What we had is a tube through which we blow. This is just the balloon connected to it, and this part of the balloon was where we had cut open this little. We made a knot, a thing in this, and we had stretched it. I'm just going to use a where's that cut bottle? So you have this is just like a amplifier, okay, and this part, when we put it around it, this part forms a little stretched membrane. This part, this is stretched. So this is your stretched membrane. So what you're doing is when you're now, I need to put the rubber band around the bottle. When you blow, this is what vibrates. The membrane vibrates, and the membrane vibrates back and forth because of the air blowing past it. And the vibrations of that are what are sort of amplified by this little horn-shaped, your loudspeaker, if you want to call it. And that's how you have this bugle or trumpet kind of sound that happens.
Is it possible to lift a rocket with a balloon and launch it from 40 kilometer altitude? Wouldn't it help a lot of food?
Would it help to launch a rocket from 40 kilometer altitude with a balloon? I don't know the offhand answer to this, because you need a stable platform from which you can launch a rocket, and I'm not sure that the fall off in gravity is going to be that much just at 40 kilometers to really make a huge difference. Also, I mean, rockets are heavy. To carry the rocket up to 40 kilometers is not going to be a trivial thing. 1 ton is reasonable, but I don't think you can have balloons that can carry much more than that to that altitude. So I don't think it's probably the whole idea for rocket is you have multi stages. So you don't have to carry the entire weight of your fuel all the way till the top. And it's a very different design compared to a balloon. So I think they are different issues. Okay, any others? That's it. No more questions on YouTube and on Facebook. Okay, in which case, thank you all for watching. I hope you could enjoy some of these experiments that we did and could follow along with us. We will definitely put up the videos of the balloon launches on our Chai and Wai Facebook page and YouTube channel. And stay safe as we unlock. Just remember, always use a mask outside, and see you again in 2 weeks online for yet another Chai and Wai session. Do give us your feedback. Do give us your feedback. Do you want more of the simple experiments that we do? Should we have more talks on, the cutting edge research happening around the world and at TIFR? Do we mix the two up? Do give us your feedback, what you would like. Till then, stay safe and have a nice weekend. Bye.